In this video, we're going to take a look at the concept of center of mass. Real objects are not simple, they're irregular. And we've been simplifying every object by just saying it's a single dot. It's in the free body diagram. And the truth is, there's nothing wrong with this, but it does miss a few things. The reason we can do this is that that dot actually represents this thing we call the center of mass. And this is the object where the point on the object where if we support it, it will balance. If you ever tried to take an irregularly shaped object and get it to balance, you understand that it only does it in certain spots, and it can be pretty unstable. This is the object where the object's mass is sort of located, right? If you had to pick a spot. And if you were to fling it through the air, that would be the point around at which it would rotate if allowed to rotate freely. So if you had some two-dimensional shape, this one kind of looks like a house or a barn or something, but upside down, and you wanted to know where the center of mass is, one way to do would be to sort of put a little pin in one side, drop a plumb line straight down, and let it hang. We know that the center of mass has to be supported, just from experience and from the definition. So you know that somewhere along that line is the center of mass. And then do it again from another spot and more if you want. And wherever the lines cross, that's your center of mass. You could also fling it through the air dramatically if you wanted to. The center of mass of a system of particles is defined as this average. Our vector here means x, y, and z all together. We normally look at one dimension at a time, but basically the idea is you take the position of one mass, and then you add the position of the other mass, and so on, and then you divide by the total mass of the system. Practically speaking, that means for an individual dimension, like the x center of mass coordinate, mass 1 times its x position, mass 2 times its x position, and so on, divided by the total mass. And you can do this in all three dimensions if you need to. So for example, if you have these three objects, 2 kilogram, an 8 kilogram, and a 5 kilogram mass spread out on this grid, well, the x center of mass and y center of mass equations are right there. And so you can start by plugging in the values. The 2 kilogram mass is at position 0 in the x, 8 kilogram at 1 meter, 5 kilogram at 2 meter, and then we sum up all the masses. We can do that same thing in the y, 2 kilogram at 0, 8 kilogram at 2, and then 5 kilogram at 1. And you end up with 1.2 meters and 1.4 meters as your coordinates for the center of mass. So that's just individual particles. But you could also do this if you have an object that has uniform density, a ball, a cube, a block of wood, something like that. And if you have multiple individual objects where you can figure out where their center of masses are, you can add them up as if they were particles at that center of mass. So here's an example of that. If you have a raft that's kind of uniform density, 300 kilograms, dimensions 4 meters by 8 meters. And then it has two 150 kilogram crates set on it as shown. If we want to perfectly balance this thing, we want the center of mass to be at the center of the raft, where should we put the third crate? Well, the center of mass of the system needs to be at 4 in the x direction and 2 in the y. That's the center of the raft. Total mass, 750 kilograms, because we're going to have 3 crates and 1 raft. We can set up our equation. The difference is just that the unknown here is the position x3. So you have to do a little algebra, plug in all your values. You can find out if you place it at 6 meters, it will balance out in the x direction. It will balance everything out. In the y direction, we can do the same thing, right? Same basic idea. And you find out that it needs to be at y equals 3 meters to perfectly balance everything out. A big application of this is if you imagine a container ship shipping across the ocean, hundreds, thousands, I think, containers, each with different products in them. They're not all exactly the same mass, density. And so the information that is recorded about each thing and where it goes has to do with mass and distribution of things and a few other things. But it's very important that you balance this so that the center of mass of this whole system isn't off to one side or the ship would tip over. We could also do this with just a system of two objects moving relative to each other. If you imagine this two vehicles driving in opposite directions, at the beginning, the center of mass of the system is right there in the middle. And when they start to move, right, we should also be able to do this. So, oops, I'm sorry. I jumped ahead and then back. 1,000-kilogram car traveling one direction, a 2,000-kilogram truck traveling the other direction. If you track what's happening here, well, we need to know the position, but what is position but velocity times time? If we're talking 10 seconds later, we multiply that by each of their velocities and we can find their position. We find out that this particular case, the center of mass actually never moved. It's still at position 0 where it was before, because the double mass car is traveling at half the speed and the half mass car is traveling at double the speed. A little video here that is an illustration of kind of how this stuff behaves. I'll move myself out of the way. This is an air track, as it will say, with two carts. And we're going to start with under the lights, where you can just see what's happening here. There's some springs between those pink and gold carts on the air track. There's a little bead in the middle, kind of indicating what's halfway between them. We won't worry about that right now, but if we watch the motion of the individual carts, right, they sort of trade off. We're going to learn more about this. You may have already thought about, collisions. These are sort of collisions and explosions happen, right? The gold one goes, then it stops, and the pink one goes, and so on. And of course, with an air track and low friction and springs involved, we're basically conserving energy here. Everything goes fine until then it hits the end and it changes direction and starts pushing back. It's sort of a complex motion, but the bead at the center, which points out where the center of mass of the system is, glows under black light. So we've turned off all the lights, and so now we're going to do the exact same thing. But this time, when the air comes on, just watch that bead. You will notice that it continues with a constant velocity, regardless of the complex motion of either cart, right? And that is because of a really interesting thing, that this system of particles, if you treat it all as one, there's nothing accelerating. There's nothing to make it speed up or slow down until it gets to the end of the track. And so the center of mass just keeps moving at a constant velocity. Just kind of interesting. All right. If objects are flexible, right, maybe a spring, or even that object that we just saw, the push me, pull you, right, the center of mass can be moved even if the object doesn't move, right? If you think about this, diving off of a diving board, you can change where your center of mass is if you want to fall over or not fall over, right? If you're standing up and you stand on one leg and you don't shift your body over the other leg, you would fall. But without really moving very much, you can shift your center of mass around so that it's supported and it works. This is also a concept that's kind of interesting. You can see in astrophysics, if you look at binary star systems, often they will always orbit the center of mass. And there's nothing there in this case. It's just the center of mass of these two stars. And when their masses are different, like, the former ninth planet Pluto, and what used to be called its moon. But this system, is orbiting the center of mass. This is true about the Earth and the moon. It's not this dramatic, but together they orbit around the center of mass. Even this whole solar system, right, the Earth and the sun, the center of mass of the whole solar system is always inside the sun because the mass is so big. But you could also get more dramatic things like this, which is pretty common for binary stars, where they're orbiting in elliptical orbits around the center of mass. We'll talk a little bit more about orbits and gravitation in a little bit, but some ideas for now. So what are the big ideas here? The center of mass is a very special point, and we've actually been using it all along. The point that we have called our free body diagram point is actually that point. And it can help us think about systems of objects, how things balance and are supported, and how they rotate.